Welcome everyone to my presentation about Project Loom and impact on Java and Kotlin. My name is Urs Peter. Because of my 20 years in industry, I dare to call myself a senior software engineer. My daily job, I try to be as much as possible with my hands in the dirt as lead developer and solution architect. I'm also a trainer at JVM Academy, where I provide a variety of trainings about Kotlin, Scala, also architectural trainings about microservices, event-driven architecture, and the like. I'm also a JetBrains certified Kotlin trainer, where I help teams in all stages of their Kotlin journey. When you look at my career, started out with Java about 20 years ago, moved about 10 years ago over to Scala, and since about 5 to 6 years, also writing my backend logic in Kotlin. Why is that noteworthy? Well, because throughout whole my career, I had a kind of passion and interest in concurrency. In Java, I did low-level threading. In Scala, I did a lot of reactive programming with actors, reactive streams, futures, and the like. And in Kotlin, did a lot of stuff with coroutines. Okay, enough about me. What I would like to know a little more is about you. So who of you is a Java-only developer? Okay, that's about something half. Who also does a bit of Kotlin sometimes, or full-time Kotlin? Oh, it's almost as much. Cool. Who of you has used these reactive frameworks, like Vecflux Reactor? Okay, that's quite a lot. Who thought this is particularly simple? Oh. There's one hand. Wow, so we have a very smart guy in the room. For the rest, I wouldn't have raised my hand either. And who has done something with coroutines in the Kotlin? Quite a few, not that many. Cool, excellent. So then let's hit the road and talk about Loom. Well, there is a question here I see, and he asks whether these Kotlin coroutines, what they're for and what problem they solve. But okay, I thought we talk about Loom, right? The nice thing about Loom is that coroutines and Loom, they have a lot in common. And because we also want to know the impact about Kotlin, we definitely need to know a bit more about coroutines. And the nice thing is that conceptually, these two concepts have so much overlap that once you understand coroutines, you will also understand Loom much, much better. So once you understand coroutines, you will also much more know about Loom. So let's go step by step. And we start actually at the place which has nothing to do with Loom or coroutines, but simple blocking code. This example I've used through my presentation in various forms. This would be the most simple one, where we do some 3 or 2 remote network calls, which all are blocking, and eventually we save a user in a database. And you might think, okay, this is so easy, so it does the job, why should I ever learn something else? Why do I need something that I probably can't see, but might be there? And the point here is that once you put this thing under load, then you might know why this particular model is not as powerful as it looks like. What I've done is I've created a Spring Boot application, which does exactly what you've seen on the slides. This is my endpoint. So I do my remote calls here, and then I store a GPA user in a database. What I can do on top of that is simply adding a delay for my remote services. So this particular remote service, once it receives this request, will wait for a given amount of time before it replies with a response. We can call this particular endpoint, and what you also see is the thread that handled this particular request. So it's just a normal NIO thread. We also can time the thing. And what we do here is we introduce a delay of 200 milliseconds. And because we do 2 remote calls in sequence, well, how long does it take? About 400 milliseconds, right? Plus a bit overhead for storing my user in the database. The interesting thing happens is when we put this piece of code under load. This is what I mimic here. So this would be this particular example. And now, instead of having only 200 milliseconds, I increased it to 2 seconds. So what I actually expect is to have an average reply of 4 seconds, right? It's because we do 2 remote calls. And I do this with 100 users concurrently. To get the dramatic effect I intend to do, I also did a little tweak, I have to say that, otherwise it's not really fair. I decreased the amount of threads I use in my application to 20. Normally it's about 200 is the default, and it decreased it to 20 to get the dramatic effect quicker. But no matter, so eventually when you have a lot of resources that would hammer my application, you would get this effect anyway. And this is exactly what you see how. So our min response is 4 seconds. It's only the min. The average is 18 seconds. 18 seconds. So it's 4 times longer plus than the average. How is this possible? In order to understand this, we need to know how these architectures look like. So these blocking architectures work with a thread pool of about 200 threads. Whenever a request comes in, this particular request would handle the whole request. So when we do some remote I/O, blocking I/O, the thread would simply wait for a reply to be received before it continues with the database. And through all this time, this particular thread is blocked. What happens now if a resource is becoming slow or we get some heavy load? And now we also get actually an element that kind of got lost on my slide. So what happens if a resource becomes slow, which is exactly what we mimicked with our example, is that the thread pool might be depleted because all the threads are waiting for this particular resource, which then leads us to the fact that we cannot accept new requests, leading to very unhappy users. Besides that, we also cannot really leverage parallelism very well because our model is sequential by default. This problem was kind of undergoing quite some time ago. This is when, about 10 years ago, reactive programming came around to actually provide a solution for this particular problem. So what I've done is I've rewritten this particular code with Project Reactor. This is exactly how it looks like. Let's see how this performs on the load. So also here, I have this particular piece of code here. So this would be the Reactor code. Then we do the same thing here. So we have a curl time. We have now 200 milliseconds delay like we had in the previous case. And what's kind of interesting is that we do not get an average of 400 milliseconds like before, but 200. Why is that? Well, with Reactor, I can quite easily leverage parallelism. My use case allows for doing that. So now I only have about 200 milliseconds plus a bit of overhead for storing my particular entity in the database. What happens if I put the thing on the load with my command line tooling? Doing exactly the same thing. So I have a delay of 200 milliseconds, or 2 seconds, with 100 concurrent users. And wow, this is exactly the result I would expect. No matter how much load I put on my system, I always get these 2 seconds on average. How is it possible? So how can this particular model perform so much better? Well, again, here we need to look at how it works under the hood. So instead of having a thread pool with 200 threads, we actually have less threads in that model. You have less threads, but you get more performance out. How is this possible? Quite simple. So whenever a request comes in, it is handled by one of the threads of this pool. And whenever it hits an I/O boundary, this thread is not simply waiting there, but it goes back to the pool. Once you get a reply, the same or other thread would be taken from the pool and continue with the processing till it hits another I/O boundary, would go back to the pool, and so on. So by doing so, a block will never a thread will never be blocked. What you cannot do is simply take this model and swap it with the blocking model we've seen before, at least in terms of libraries. You cannot do that. When you go for the reactive model, you have some constraints, in the sense that you should use non-blocking libraries. So speaking in Spring Boot terms, you should use a web client instead of REST template, or RTDBC driver instead of GDBC, which limits the choices of frameworks you can use. Should you not do that, I mean, people maybe don't do that, then what you will get is that one of these few precious threads here would be blocked, which actually would exhaust your thread pool extremely fast, much faster than in the blocking model, because there were 200 threads. Here we have about as many threads as we have cores. So what you have to ensure all the time is that when you do these kind of blocking I/O operations, you have to have a separate thread pool available that has enough threads you can spare for these kind of operations. Otherwise, you shoot yourself really in the foot. So that's something you have to be very, very cautious and aware of. So, assuming we do this all right, so we use a non-blocking library, if such a resource becomes slow or we get some heavy load, well, our system still can accept the requests, right? Because the threads are not blocked. Besides that, we now can leverage parallelism, and well, this leads us to happy users. All problems solved. If that was the case, I think the presentation would be over. We could all go home and rewrite our applications using a reactive programming model. The problem is that these reactive toolkits, they are based on the library level. And the abstractions they give you, they really have a tremendous impact on your code. They go viral in your code. So all of a sudden, your code is not anymore about the business logic, but it's about monos. It's about zip, flat map. So the business intent of my code really is getting lost. Besides that, I cannot use normal programming constructs like throwing exceptions, try, catch, and the like. I have to use the kind of DSLs this particular toolkit offers me. Another toolkit, Reactor, or maybe another one like Uni from Quarkus, does this again in a quite different way. So I have to relearn everything over and over again. And we've seen you can shoot yourself extremely simple in the foot. If, for instance, you use a blocking call accidentally, the unit test will be fine, but in production, you get the problems. And then figure out what went wrong. Good luck. So we can say the reactive model solves the problem from a runtime perspective, but imposes a really large burden on our code base. So the accidental complexity, so to say, is really tremendously high. So is there a better answer? I would say yes. And this is where the coroutines come in. So what are coroutines? Coroutines allow you to express your logic sequentially, whereas the underlying implementation figures out the asynchroncy. The only thing you would have to do is you have the same methods, but mark them as suspend, in Kotlin, of course. And then, well, we simply call these methods in sequence, and the underlying code would be executed in an asynchronous fashion. And because I really am sure that your boss would understand this piece of code, I think this must be maintainable code. But now it performs as well as the reactive counterpart. I also can leverage parallelism quite easily. I can use async await, a construct that is found in many languages, and by doing so, I actually have, as said, the best of both worlds. Well, is this a total hassle-free experience? To a large degree, but not fully. We still have to kind of interact with things like Suspend, like this Coroutine scope. So I think we need to dig a little bit further to know what we actually encounter once we embrace this particular model. But before we do that, let's first look at what are coroutines. When you look at the operating system, you have at the lowest level, you have CPUs, right? And on top of that, you have the so-called kernel threads. A kernel thread fights on a time slice on a CPU by means of so-called preemptive scheduling. You might have heard this term. Kernel threads are quite an expensive resource. So you can have 4,000 kernel threads per gigabyte of memory. That's not much. When you look at a JVM, what you see is that JVM threads are mapped one-to-one to kernel threads. So they're as expensive, so to say. Coroutines is simply a layer on top of threads that are much more lightweight. So you can have about 2.4 million coroutines per gigabyte of memory. Eventually, also, coroutine needs to be executed by thread, because when you want to execute stuff on a JVM, you need a thread, right? But a thread is not bound to a coroutine. So one thread can execute multiple coroutines, and a coroutine can be executed by multiple threads. So let's see, what is the difference in terms of code and definitely also performance? So here, you have a simple example, again, using some slickness Kotlin offers us. This block here creates new thread, new runnable, and this would be the run method. But then with such a code block. So we spin up 100,000 threads, sleep for 2 seconds, wait for all threads to be terminated. The counterpart in Kotlin would look as follows. What you cannot do in Kotlin is create threads like you could in Java with new thread. You always need a builder for that. The builders we use here is run blocking, which is a special one. You should use it in production. You should only use it for testing purposes. There's the word blocking in it, right? Kind of should initiate your warning signs. But we will see why this is needed. Apparently, we need some context to make, well, to really spawn coroutines. Here, we really spawn coroutine launch. And then the first beautiful thing happens, which is delay. Instead of blocking the thread with sleep like above, delay simply suspends the coroutine and resumes it once the particular amount of time has passed. So what do you think? What will happen if we execute this piece? Will it work? Will it not work? Who thinks it will not work? One person. The rest thinks it works? Okay. Seeing is believing, right? So I have also here this particular example with the many threads. So I create 100,000 threads. Let's run this thing. And what you see, we get an exception after 8,000 threads. Well, that's logical. We just seen that you can have about 4,000 threads per gigabyte of memory. My JVM has 2 gigabytes of memory. So after 8,000 threads, I get out of memory. Right? Finished. Let's do the same example with coroutines. We've seen that you can have about 2.4 million coroutines per gigabyte of memory, so this should be a piece of cake for the coroutine case. And that's also what you see here. So create the 100,000 coroutines in 2.9 seconds. So boom, and a piece of cake. Let's take a closer look at these suspend functions. When you mark a method with suspend, then you gain the capability that it can be paused and resumed at a later stage. That's the beautiful thing about suspend functions. But they also introduce a constraint. So if you have some layered architecture, control, service, a processor, maybe a client you use, then you cannot call from a non-suspend method as a suspend method. You would get a compilation error. So this case is not possible. What you could do, and what people do, but they shouldn't, is you could use these run blocking blocks. Then you could call a suspend method. But as said, then you still block threads. And when you have a true reactive application, you don't want anything to block. So the way you should do it is start right away with suspend. So start right away with the Coroutine. And the good news is that all the frameworks out there, the Quarkus, the Spring Boots, the Micronauts, and so on, they all have support for that. So you simply can mark your controller as suspend, and then it will figure out to give it the right context so that you can start with suspend. And from there on, you can then call other suspend methods, and you can also call normal methods from suspend methods. And this is the same like with reactive programming. Should you do some blocking I/O call so that this precious scheduler thread would be blocked, you also have to ensure that you provide a thread pool that is dedicated for blocking I/O, that you won't waste the scheduler threads. So the same applies here like reactive toolkits. You have to be aware of that. Okay, so these are these builder methods. And when we look closer at them, you see kind of two interesting constructs, the Corridine Context and the Coroutine Scope. And this is interesting, because when we look at Loom later on, you will see these concepts coming back in a slightly different shape. But once you create something like this, you eventually end up with these kind of core building blocks. So I think it is worthwhile and valuable to understand a bit more how these things work and what they do. Let's first look at the Coroutine Scope. And let's look at the case where we don't have a Coroutine Scope. So here we spawn a thread, and we don't want the program to exit before this thread has been completed. What do I have to do? Well, what I have to do is I have to join, right? Which is kind of evil, because here I block, and if I don't block here, the thread will never terminate, my program would terminate. So I have to synchronize my different asynchronous processes manually, which is quite tedious. And here actually this Coroutine Scope comes in. So scopes work as such that this actual run blocking gives me is this Coroutine Scope implicitly available. That's a feature only Kotlin has, Java doesn't have it. From there, I can then launch a coroutine, and here I get another scope, which is a child scope. So what do these scopes do? Well, the parent scopes, they supervise the completion of the child scopes, no matter how deep I nest my process trees. So this scope will always supervise all the child scope and kind of not exit the program before they're all completed. That's what they do. And that's a beautiful and very powerful concept called structured concurrency. You might have heard this term. I can even add additional structure in my code. I could say, okay, I first have this block before I print done, for instance. So by simply giving structure to my code, I can kind of manage my concurrency. And the beautiful thing about this example is that here, nothing blocks. Nothing. It's only suspend and resume. Structured concurrency is really tremendously powerful at least in Kotlin. So what you also have, say we have a tree of processes. So these are not normal sequence diagrams, these are really separate processes, separate coroutines, like separate threads conceptually. What I can do is I could, for instance, cancel one of these tasks, and then all the others would be cancelled automatically too. So cancellation propagates down my tree. Of course, if I don't want a certain process to be cancelled, I could exclude it, which we see in Loom is not possible, but with the Coroutines it is. How about exception handling? Well, also exception handling works in a structured way. So when a subprocess throws an exception, then the parent scope would kind of catch it, or you can catch it, and nothing else would happen. So exception handling works like in a synchronous world, even though it's totally asynchronous world. That is really awesome. If we had threads here and they throw an exception in this thread, it would just disappear in limbo. You wouldn't get any notification of that. And the nice thing is that exception handling and cancellation also work nicely together. So by default, if I have an exception going on and don't do anything, it would simply propagate up my hierarchy, and the hierarchy would then simply cancel all the processes that are beneath it. So this is what would happen. And of course, also there, I can nicely customize it to my needs. I could say, I have a certain scope that doesn't care about the exception. It wouldn't propagate it on top. So we have fine-grained control how you want to deal with a variety and multiple processes. So this was the coroutine scope. Now we look at the next building block, which is the coroutine context. We've seen that for coroutines to be executed, you need a thread pool. And this is basically kind of represented with this coroutine context. We can pass a so-called dispatcher. You always get a default one, so you don't have to pass it manually. You just get a good one, and if you want to change it, you can do that, which is what we do here. So here we have another example where we call two remote calls in two asynchronous processes. And because they're blocking calls, I have to ensure that I have enough threads available. And this is where I then would pass in such a dispatcher's I/O on top of that. And the nice thing about this coroutine context is that it automatically propagates to my children. So without specifying anything here, it would get the context I set on top. I can change it if I want, but I get this automatic propagation, which is very, very powerful. And if you look closely here, we do something fancy, right? We do something with an MDC. Have you heard of an MDC, most of you? This is a diagnostical concept. So what you can do with it is you put this in, and then you're logging, this particular ID would be logged. That's what you want. But here, we have a dispatch I/O, so multiple threads. So the threads where we put this MDC on is not the same thread that execute these things. So we don't get our MDC propagated there. And also there, Kotlin found a beautiful way to kind of bridge the thread world with the coroutine world, with the so-called thread context element, for which they have a default implementation for MDC. You simply say with context MDC, and then we would copy from this particular thread the data through, and then also give it to the coroutines. So in this case, we can ensure that our state is propagated properly to the underlying coroutines. Okay, you might think so far so good. These coroutines are kind of a separate world, but sometimes you have to interact with some reactive framework or asynchronous library. How does this work? Well, quite simple. So if I want to rewrite this code into coroutines, the only thing I have to do is the following. I mark my method suspend. I use one of these extension methods of Kotlin, which lifts my mono into a coroutine. That's the only thing I have to do to get rid of the mono abstraction. Now the mono abstraction is gone. I'm only back to real business domain objects. So by using this approach, all this kind of complexity we have here, we simply can convert it into that. The only thing I have to do is use suspend. And well, just to kind of show you that this really performs as well, so this would be the code here, written in Coroutine. So you have this suspend keyword in Spring Boot. And let's do the performance test right away. Again, with 2 seconds delay, with 100 concurrent users, and you see you get about the same, so 2 seconds average. And here we had also about 2 seconds. Depends with how many times run. So the performance is really equal. There is no additional overhead involved by using this particular approach. Okay, So let's recap. We've seen that with coroutines we have lightweight threads. We can write our logic synchronously, which is executed in asynchronous fashion. It is intrusive to a certain degree because we have the suspend methods, and you cannot just call a suspend method from everywhere. This is a kind of disadvantage we have here. We have great structured concurrency, and interop with reactive frameworks really works very, very well. So all in all, this is really what you get with coroutines, hassle-free concurrency. No wonder that Java wants this too, and this is where project Loom comes in. So let's go and explore Loom, and the nice thing is we already have the list to look for what kind of features we expect in Loom to be available. So what is Project Loom? First, some facts about it. It's a project which is quite old by now, 5 years old, they're doing it. And when you look at the definition, you see that the goal is the exact same like with coroutines. So easy to use, high throughput, light recurrency model for the JVM. So try to achieve the exact same thing. But the way they are going to achieve it is really different. Loom is not one thing. Loom is actually divided by 3 different chapters. The first chapters are virtual threads, you might have heard of them. And they're very similar to coroutines. This one is getting final at the end of the year. So at the end of the year, we all can enjoy virtual threads. Then there are 2 other chapters which are still incubator phase, which is structured concurrency, which are similar to coroutine scope, and then the so-called scope values, which are similar to or slightly similar to the Corridine context. So first, let's take a look at the virtual threads. So what are virtual threads? Virtual threads are, as I said, very similar to coroutines in the sense that they're lightweight threads. You can have millions per gigabyte of memory. But also, virtual threads need to eventually be executed by a real thread. And instead of using a platform thread, GDK21 has the so-called carrier threads. These are threads you're not aware of. For you, they don't exist, but they do the real work. And of course, you still have classic threads available. So how does such a virtual thread look like? This was the example with a normal thread, and ta-da! This is the example with a virtual thread. And when you look closely, what you see is that, well, it's still thread, right? So from the outside, there's no difference. It's a thread. Interesting. Interesting design decision. So what's the difference in terms of performance? This was our Coroutine example we just executed before. Now we changed our threading example by using a virtual thread instead of a normal thread. And what do you expect to happen? This is what I do here. I run it, and we expect, I assume, that it simply will work as expected. So we created 100,000 virtual threads in 2.3 seconds. So in both cases, it's easy like pie. So the really interesting thing here is that sleep now behaves really different. It's the same sleep like before, but because we run with a different thread, it behaves actually like the coroutine delay, where stuff is suspended and later on resumed. So lightweight threads, we definitely can tick the box, right? Let's go on. Can you write synchronous logic asynchronously? And this is really the tremendously cool thing about Project Loom. Let's do a recap. We've seen that when you do coroutines, also reactive program, you should use non-blocking libraries. You should use Java and IO, which also gives some impact on which library you can use, right? We've seen it, you should use R2DBC instead of GDBC, and so on, and so on. You can still use blocking code, but then you have to ensure that you have a dedicated thread for that. If you don't have it, then we've seen what happens, right? So the thread will deplete, and your performance will really deteriorate tremendously. Now, the wonderful, really awesome, cool thing about Loom is that they retrofitted these kind of old-fashioned APIs we try to work around in our reactive model, which namely is Java I/O and Java do concurrent, because these things, 2 blocking things, as such that whenever a virtual thread calls them, the underlying carrier thread wouldn't be blocked. So the virtual thread, like a coroutine, would be kind of paused and then resumed later on. They call it parked, give it a name, suspend, park, pause, whatever. So the real thread won't be blocked. Only the virtual thread would be kind of put aside, and once you get a reply, it would continue working. so that these carrier threads are always able to perform their tasks. There are two exceptions, though. If you have synchronized blocks, or you do make native calls, you will block carrier threads. So this is evil, and that's what I personally think is why many frameworks don't yet have embraced virtual thread fully, because they still have in their code base some synchronized block somewhere, and they should be rewritten. You can rewrite that using Java to concurrent read or write locks. So for me, this is really the best Back to the Future moment in real life I've seen so far. Something that is old, kind of everybody wants to get rid of, gets a new life. Hard to believe, right? But I can prove it. So what I've done here is I have the same Spring Boot application, I have some configuration, and now I restart the Spring Boot application so that it will handle its requests with virtual threads rather than normal threads. Because well, from the outside, it's still a thread, right? So the application has no notion of it. It's just a thread. So here we started. Let's do a call. The same blocking call we did before, the very same. So curl. And then we also are going to prove that it's really a virtual thread in there and not some other magic. So here you see virtual thread. The virtual thread has handled this request. Let's look at the timing. So how long does the timing take? We have a delay of 200 milliseconds. Well, it still takes our 400 milliseconds because you don't do things in parallel. It's just the example we had in the very beginning, right, with the 400 milliseconds. And now let's put this thing on the load. Exact same thing with our 2 seconds delay, 100 concurrent users, and what you see is the result you always wanted, which is now on average we get these 4 seconds, what we always aim for, right? So only by changing a bit of configuration, now all of a sudden my application performs so much better. How is it possible? Well, this model doesn't use thread pool. I mean, eventually it does, because these carrier threads are not unlimited amount of carrier threads. They will be kind of pooled somewhere, but this is transparent for you as a developer. It's just a given, it's there. And you might configure it, but it's not something you can kind of access. Of course, always an online carrier thread would do the work. Whenever you hit an I/O boundary doing blocking I/O, which is fine, this carrier thread wouldn't wait. Only the virtual thread would kind of be suspended, would go back to its carrier thread place. When you get a reply, maybe the same another carrier thread would continue, and so on until the reply is served. And also there, if a resource is getting slow, well, we always can accept new requests because nothing is blocked. Can we leverage parallelism? Let's see. Apparently not yet. We just had this blocking example. Let's see it later. But definitely our performance got better and we get happy users. So that's really the cool thing about Project Loom, is that it's totally non-intrusive. You're not aware of it. It just does its job. And so should you use this thread per request application, and I assume many of you do, unless you do reactive stuff, well, then you're good to go. You simply switch to JVM 21, and woo, you get a performance boost for free. A lot of less CO2 for the world. Will last about 10 years longer, 10 years longer definitely. Okay, so now let's look at these two things, and this is where things get a bit more experimental because it's still incubator phase. Even though I'm monitoring things closely, they haven't changed that much recently. So there is quite a big chance that what you see here will be what it will get eventually. But still, that's the disclaimer. So here we've seen in Kotlin, you have these Coroutine scopes, and then within such a scope, I can launch a tremendous amount of processes, and it will ensure that they are completed first before we continue, right? That's what we've seen before. The counterpart in Project Loom with JEP 428 looks as follows. This is the code you would get. And now you see that they solve to a certain degree in a similar fashion. They also have a scope. They don't call it a Coroutine scope, they call it a structured task scope. But the concept is similar. It's a bit a leaky concept because, well, you have to call join and throw a fail, and if you forget to call this, then you get all kind of runtime errors, but okay, eventually you will manage. So the concept is similar. What they also had to find is a kind of a way to give the boundary which kind of process need to be terminated before we continue. And this is where they chose for the try with resource block in Java. Because they don't have, like in Kotlin, this kind of code block language features. So Java had to come up with something else, so they reused this kind of try with resource blocks. So this is going to be terminated first before this piece is terminated. How about async await? well, also here, something fancy happened in the sense that the bad old future, remember me, the future from 1.7, the one with this ugly get method, which always blocked the thread, which was really kind of banned, is back to the future. Because if you call .get with a virtual thread, the underlying thread, Coroutine, won't be blocked, right? Also there, we got a kind of improvement. So if you want to do async await with Loom, this is your vehicle. It's the bad old future. How about cancellation? Well, cancellation kind of works. So you have cancel methods here, but cancellation in Loom has to rely on thread interruption. And that's a limited way of doing cancellation. But this is how Loom solves its problem. It's on the thread level. So they have to use the infrastructure there to do these kind of use cases. So you can, for instance, cancel certain of these task scopes, but what you cannot do is, for instance, exclude things from cancellation. And you might think, okay, is this a big deal? Well, it is. If you write frameworks, you sometimes want resources to be cleaned up before you close stuff. And this is something you then couldn't do in Loom. And that's probably also the reason why on the website they say, maybe we're going to change it later on, but that's going to be hard, because I said they are on the thread level, they have to run interruption. If you do something else, that's why they didn't choose for something else, right? So that's going to be interesting. How about structured context propagation, the Corridine context we've seen so far? So here we have this MDC, and then, for instance, we have this MDC context so that we can propagate even thread local state to new coroutines. Kotlin has kind of written hooks for that. This is where I think, Loom guys, you should maybe go back to the drawing board. This is how they address it. They have this so-called scope value, which then has this work class where you provide this particular value with a particular value, which you then can retrieve no matter how many processes you spawn. So within this particular code block, lambda, you have access to this variable no matter how many processes you use in there. I mean, when you look at it like that, it sounds like a good idea, but when it comes to interop with existing frameworks that still heavily rely on thread locals, that's going to be a nightmare. Because you cannot propagate thread local state easily to other kind of these scopes. I mean, we will see it later on. You can, but you have to do it manually. So I really hope that they will go back to the drawing board and make it possible also thread local state. I don't like thread local state, by the way. I kind of hate it, but well, frameworks use it, so you have to deal with it. And Java has a good history in backwards compatibility, so I hope also they will address this in a better way. So structured concurrency, okay-ish. Let's look at interop with reactive frameworks. Well, the good, bad news is that all this reactive stuff just can put in the waste bin once Loom is there. All this complexity, all the knowledge we acquired, you don't need anymore. When you use structured concurrency, this is how you can do it, without in a sequential way, rather than flat maps, all this kind of callback way of doing things. No more mono abstractions, just normal code. How about Reactive Stream? Well, their story is different. Loom solves the problem at the thread level, and threads do not have the capability Reactive Streams offer, like back pressure. That's really a concept that's only available for Reactive Streams. So there you still have to use one of these abstractions. So for this is Reactor, this is Quarkus, this is Vertex or Micronaut. They use these different kind of toolkits, which are kind of complex. For Kotlin users, there is good news, because you very easily can convert any of these to a flow, which is also a construct that is close related to coroutines. Much simpler than these, really, much simpler. So once you learn flow in Kotlin, no matter which framework you use, you're good to go. But still, you have to use an abstraction like that. Loom won't solve that for you. So interop with reactive async frameworks, moi. OK, so let's see. If we compare Loom to coroutines, we see more or less this. This we see in coroutines. It is intrusive to a certain degree. Writing synchronous logic is even better, because we don't have to care about anything. It's always non-blocking no matter what. And the structured concurrency and interop is better with coroutines. So it's a bit a mixed image of the information I presented you today. I think what's getting very interesting is when you would combine Loom with the features Kotlin offers. And we'll look at that what this would mean. So if you're a Java developer and use Loom, this is more or less what you get, right? So you now can make blocking calls which are non-blocking. That's awesome. You can use for parallelism this structured task scope, and then, well, if you don't do too fancy things like propagation of context, you would be fine. You have to be aware of the leaking API, and of course you still have your exception handling, which most of the time just gets in your way. It's annoying. If you want to have something like propagation of thread local, well, this is what you have to do. Do it manually. You have to copy-paste thread local state from one scope to another. Tedious, but doable. What's nice in Kotlin is because we have this language feature of these code blocks, I could write a little bit of glue code to make it look a bit like a coroutine. Right? This looks a bit like coroutine code. And the only code I've written is this piece of glue code. So by having certain language features, it makes it much more bearable to use Loom in Kotlin. Except that we still don't have thread local propagation and so on. So all these limitations we still have. So we've seen that Loom has these limitations. So the context propagation is an issue. We have these scope values, but they don't really pay off. And also cancellation has its limits. So there's still some fundamental stuff is missing with Loom when you go to the extremes, right? When you do keep it simple, that's fine. But you go to the extremes, you lack stuff. The interesting thing here is that a coroutine needs to be executed by a thread. But the thread can also be a virtual thread. It's the same interface. The coroutine has no notion that a virtual thread executes it. And I think this is where the sweet spot comes in. So now we can use all this propagation stuff. So this just works with coroutines. We can propagate our thread local. We can use blocking APIs now without using this dispatch or having the chance that we shoot ourselves in the foot. It's all unnecessary anymore. Just works. And I have now all the nice context and cancellation propagation I always wanted. And on top of that, this stuff I can use at the end of the year in production. Because all the other structured concurrency stuff, yeah, it's still incubated. It might still take a while till it's available. So, a bit of a conclusion. If you have simple applications, I think Java and Kotlin would benefit equally from Loom. So the thread per request applications, where you don't do fancy stuff with parallelism and so on. Then they're just there's no difference. When it gets more advanced, so if you heavily use structured concurrency, Java will also profit from it, so it will definitely get simpler because you can kind of say goodbye to reactive frameworks, except the streams, but use kind of more sequential way of expressing your logic. But I think because of what we see, because of the language feature Kotlin offers, and because the coroutine's rich environment for cancellation and so on, combining them with virtual thread is really the sweet spot. Okay, so I think I have a bit of time left to finish up with what you do with the knowledge you gained today so far. Well, what I think is very important is to ask yourself, do you really need high throughput and parallelism in your application? Because I think we often also write applications that are for administrative purposes. They don't have millions of users, of thousands, of 100,000 of users. Just, well, software some people use. And there you don't need to have you don't have the need to have all this absolute efficiency. If this is the case and use Java, then I would advise you, stay with your blocking model. Don't do something reactive. Because once Loom comes along at the end of the year, you get your performance boost anyway. Should you really have a business case, a use case for this, and I have applications written that had this case, then I advise you use Reactive Stack, except that, well, if structured concurrency comes along, you probably have to rewrite a lot of stuff. In Kotlin, it's similar. So if you don't need it, don't do it. Simply do stuff in a blocking way. That's also really the way I do it in my projects. If it's not really needed, just go blocking. And if you need it, well, in Kotlin, always opt for coroutines. Don't use reactive toolkits, because as said, it's a way more simple model to kind of master. So also people that are not very knowledgeable about these kind of concurrency elements can handle this model way better than the reactive library model. And once Koom comes along, then you kind of get a completion of what coroutines already offer for you. So the bottom line is, when you use Kotlin, don't use a reactive stack, because this will eventually turn into legacy. Okay, I think I'm more or less within time. This was my presentation. Thank you.